Thank you. Thank you for inviting me. Thank you for introducing. I'm going to talk about Ehrhart H-star polynomial. One of them is based on my work on positroid polytopes, and the other is based on my joint work with Elizabeth Bullock, who is a graduate student at MIT, and we worked on alcove polytopes. Here is an overview. I'll first talk about Ehrhart theory and then introduce positroid and alcove polytopes. Then I'll describe their circuit or alcove triangulation, and then present the main results on H-star polynomials. Then for application, I will first talk about a relation with decorated order set partitions, and then application to tree positroids or half-open positroid polytopes. So Ehrhart polynomial, let P be a lattice polytope. The Ehrhart polynomial is the number of lattice points in the dilation, and Ehrhart showed that this number is a polynomial in the dilation, in terms of the dilation. So if we put it into a generating function, then it is a rational function whose denominator is very simple, and the numerator is the H-star polynomial. Stanley showed that the H-star polynomial has degree at most d with non-negative coefficients. Therefore, we might try to find some combinatorial interpretation of it. So, for example, the standard d-dimensional simplex has Ehrhart polynomial equal to this binomial coefficient and H-star polynomial equal to 1. And the standard d-dimensional cube has Ehrhart polynomial equal to 1 plus t to the d. Here is a literature review on the H-star polynomial of hypersimplices. So the hypersimplices are matroid polytopes of the uniform matroids, which are also positroids. Positroids are those matroid polytopes who are also alcoved, and therefore, hypersimplices are kind of the first example that we would care about. And Kazman computed the Ehrhart polynomial of the hypersimplices using Veronese algebra. Ferroni showed that they are Ehrhart positive. Nan-Li computed the H-star polynomial of the half-open hypersimplices, which are hypersimplex with some facets removed. Nick Early conjectured that the H-star polynomial of hypersimplices are counted by what he defined as the hypersimplicial decorated ordered set partitions, and Donghyun Kim proved it. The question we're trying to answer is we want to give a more combinatorial formula for the H-star polynomial of positroid polytopes or the Ehrhart series of an arbitrary alcove polytope. Also, we want to relate our formula back to Nick Early's combinatorial object, which is the decorated ordered set partitions. So let me introduce matroid. A matroid is a pair of a finite set and a collection of subsets called the bases. The bases satisfy the exchange axiom, which means that if we take any two sets in the bases and any element in the first set, then there exists another element such that if we exchange them, we get another basis. All the bases have the same size called the rank of the matroid, and the matroid polytope is the convex hull of the indicator vector of the bases. Here is an example of a matroid coming from matrix and also its matroid polytope. So given a K by N matrix of rank K, the subsets of columns giving non-zero minors form the basis of a matroid. In this particular example, all the minors are non-negative, therefore this is actually a positroid. And if we take all their indicator vectors, we found this pyramid shape. Positroids were first considered by Posnikov in his study of the positive Grassmannian, and positroids are matroids given by matrices with non-negative maximal minors, just like in the previous example. So they are in bijection with several interesting classes of combinatorial objects, including Grassmann necklaces, decorated permutations, and equivalence classes of Playbit graphs. Here, we show an example of the uniform matrix 2, 4, so of rank 2 and size 4. Uniform matrices are positroids, and this is like octahedron, I guess. So up to here, is there any questions? Okay. So alcove polytopes are, I guess, they appear everywhere, but this term kind of first appeared in the paper of Lemon-Posnikov. We consider an affine Coxeter arrangements with respect to an irreducible crystallographic root system phi. The regions of these affine Coxeter arrangements are simplices called alcoves, and a bounded convex union of these alcoves form an alcove polytope. Let the simple roots be alpha and the fundamental co-weights be omega, and the highest roots be like this linear combination of simple roots. Then the fundamental alcove is conventionally chosen as the convex hull of these points, and reflecting the fundamental alcove in the space would give us the affine Coxeter arrangements. Positroid polytopes are exactly those matroid polytopes that are also alcoved. So there is a little technical nuance here. We really only give a formula for the H-star polynomial of connected positroids. So a connected matrix cannot be written as the direct sum of two non-empty matrices. But also, if a positroid is written as a direct sum of other matrices, then each component is a positroid. This is shown by Ardila, Rincon, and Williams. If the matroid polytope, if a matroid is a direct sum of other matrices, then the matroid polytope is a direct product of all these other matroid polytopes, and the Ehrhart polynomial is also a product of all the other Ehrhart polynomials. Therefore, we argue that it suffices to give formulas for the H-star polynomials of all connected positroid polytopes. So to state the main results, I have to define what is a Grassmann necklace. Let k and n be positive integer. A Grassmann necklace of type Kn is a sequence of k subsets of 1 through n, such that for any I, either the next one is obtained from the previous one by an exchange, or if I does not belong there, then they should stay the same. So Posnikov showed that there is a bijection between positroids of rank K and Grassmann necklaces of type Kn. An example would be shown here. So if we let J be the Grassmann necklace 1, 2, 2, 3, 1, 3, 1, 4, then the basis of this positroid is 1, 2, 1, 3, 1, 4, 2, 3, and 2, 4. And I believe it corresponds to the pyramid example that I showed before. So to give a more, I guess, alcoved flavor of things, we will introduce what's called a circuit. Lemon-Posnikov defined a circuit to be a sequence of binary vectors such that the latter one is always obtained from the previous one by a shift of one step to the right. The positions of the shift in a minimal circuit give rise to a long cycle in the as a permutation. Parisi, Sherman Bennett, Tesler, and Williams showed that the circuits of a long cycle can be recovered through its cyclic left descents. Each circuit defines a simplex, or equivalently a type A alcove. They together triangulate the hypercube, the set of circuits of length n with k1s triangulate the hypersimplex. For example, the binary vector shown here is a circuit of the permutation cycle 32145, and that's because the second binary vector is obtained from the first binary vector by shifting the one in position 2 to the one in position 3. And then if we just follow along, it'll give exactly this long cycle. So here is a circuit description of the alcoves. For a permutation, an index I is a cyclic left descent if either it is a left descent, which means that I appears to the right of I plus 1, or if we view it cyclically, then this is still true, like if it is n and 1 appears to the left of n. So we will denote the set of cyclic left descents by CDS. Let W upper A denote the cyclic rotation ending at A. We will define this I notation to be the set of cyclic lefty sense of W, where R is rotated to the end. And this all of these data only depends on the cycle. And then we'll call all these set of left cyclic descents as the circuit of the simplex delta W, which is like the convex hull of their indicator vectors. The example is from the previous slides. So the binary vector here is a circuit of the permutation cycle 3, 2, 1, 4, 5, and they will form the vertices of delta 3, 2, 1, 4, 5. The I order on the set is the total order where I is viewed as the smallest element. For ij in N, the cyclic interval is from I to j, but order everything cyclically. So the definition of cyclic lefty sense actually extends to the restriction of a permutation to any alphabet given by some cyclic interval. For example, we can consider this long cycle 3, 2, 4, 1, 5 and restrict to the letters 1 to 3, then we get 3 to 1. And if we restrict to 3 to 1, then we consider the letters 3, 4, 5, 1, and we get 3, 4, 1, 5. And the set of cyclic lefty sense is defined very similarly by looking at like whether I is appearing after I plus 1. So what I show, the first result is that if we take a connected positroid polytope with associated Grassmann necklace J, then if we order the elements in each set in the Grassmann necklace by the I order, then the positroid polytope is triangulated by W simplices where W have to satisfy these inequalities given by cyclic lefty sets. Are there any questions up to now? Okay. So the proof idea and also later on the results on alcove polytopes depends on the notion of Schelling order. A Schelling of a simplicial complex is a linear order on its maximal simplices such that for each I, the set of intersection of the new thing with the union of all the old things is a union of facets of GI. A triangulation of a polytope is a polytopal complex with underlying space equal to the polytope such that everything in the polytopal complex are simplices. Every alcove polytope comes naturally with a triangulation by alcoves, and therefore positroid polytopes comes with the triangulation by W simplices, and they are also alcoves. The alcove triangulation of positroid polytopes coincide with the circuit triangulation that we presented just now. And Stanley showed that if a polytope has a unimodular triangulation, which means that the sort of the normalized volume of each of the simplex is equal to 1, then the H vector of the triangulation is equal to the H star vector of the polytope. So therefore, it seems like we need to really consider this triangulation complex, and here is the way we consider it. Let P be an alcove polytope with root system phi. We construct a weighted graph such that the vertices are the closed alcoves in P, and the edges are between alcoves that share a common facet. Let alpha be the simple roots of the root system, and omega be the fundamental co-weights, and then let AI be the coefficient of alpha in the highest root. Then we will give the edge A prime a weight of Li if the facet between if the facet, which is the intersection between A and A prime, can be transformed to a facet of the fundamental alcove under the action of the affine Weil group, such that omega I divided by AI is the vertex that does not belong to this facet. Where in type A, all of these edge weights are equal to 1. So here is an example On the left, we have the fundamental alcove for the root system B2. And on the right, we have an alcove polytope and its dual graph drawn in colors. So the blue edge is between, I guess, the shorter edge of the right triangle and the vertex that does not belong to this facet is 0, 0. Since they are all integers, we're fine. The edge weight is equal to 1. But the orange edge is along this longer kind of hypotenuse, and the vertex that does not belong there is 1/2, 1/2. Therefore, we would give this edge a weight of 2. So let gamma be any undirected graph and V naught be a vertex of gamma. We define the breadth first search order of gamma with root V naught be the partial order such that U, the vertex U, is less than the vertex V if and only if there exists a shortest path from V naught to V passing through U. In other words, we view the dual graph of the alcove triangulation as the Hasse diagram of the pole set that's defined by this breadth first search order. For alcove polytopes, this is the weak order of the affine well group with the specified alcove being the identity. So following Bjorner's argument, Elizabeth and I showed that any linear extension of the breadth first search order is a Schelling order of the alcove triangulation complex of P. Here is the first main result on the H-star polynomials of connected positroid polytopes. So since all the edge weights are equal to 1, the actual thing that we care about turns out to be cover. So let Pj be any connected positroid polytope where J is the associated Grassmann necklace, and let gamma J be the dual graph of the circuit triangulation for any alcove, for any permutation that such that delta W is inside this positroid polytope. We let the curly P be the breadth first search order on the dual graph with root W naught. Then the cover statistic gives the H-star polynomial. So it's a sum over all the permutations, and the cover is equal to the number of elements covered by W in this pole sets. So then Elizabeth and I worked on a generalization of this result. Let P be an alcove polytope and let gamma P be the dual graph of the alcove triangulation of P with edge weights given by Lis. Fix an arbitrary alcove A naught in P and let curly P A naught be the breadth first search order of gamma P with root A naught. The Ehrhart series of P has denominator equal to this product of 1 minus Z Li, which this part is pretty classical. It comes from Stanley. And the numerator is equal to summing over all the alcove in P, where the weight is equal to the sum of the weight of the edges between A and the alcoves it covers in the pole sets. So Carolina Benedetti and Nauer and Valencia Porras proved the type A case in their 2023 paper on lattice path matrix using geometric arguments. Here is an example. So we show a generalized hypersimplex for the root system B3 with k equals to 2. Then we draw its dual graph as shown, where A naught is chosen to be, I guess, the one that's facing us. The Ehrhart series is equal to, well, the numerator is 1 plus z plus 3z squared plus z cubed. And the 3z squared come from the 3 orange edges, and the cube come from the 2 blue edges pointing to the same vertex. Is there any question about this example? Okay, cool. Here is another example for the positroid. So we show the graph of the circuit triangulation of the positroid polytope associated with the Grassmann necklace as shown, which coincides with the Hasse diagram of the pole set if we set 2, 4, 1, 3, 5 to be the root. The H-star polynomial is 1 plus 4z plus 3z squared, and that's color-coded as in the figure. So changing topic to decorated order set partitions. A decorated order set partition of type Kn it is a cyclically ordered set partition along with the decorations, which are positive integers, such that each Ri is less than or equal to the cardinality of the set -1. The winding vector is some n-tuples of integers, such that I guess there were some definitions, but it's easier to explain with examples. The winding number is equal to the winding vector added up together divided by k. Here is an example. So we draw the cyclically ordered set partition on a circle such that the arc between them are given by the decorations. And then the winding vector is really the distance that you travel by walking clockwise from 1 to 2, and then 2 to 3, 3 to 4, so on and so on. And the winding number is equal to how many times you go around the circle when you get back to 1. So is it clear, this example? Okay. So the theorem that are conjectured by Early and proved by Kim is that the number of hypersimplicial decorated order set partitions of type Kn and winding number D is equal to the dth entry in the H star vector of the hypersimplices. Here is an example in terms of delta 24. The winding number is equal to 0, 1, 1, 2, and exactly the H star polynomial of the octahedron is equal to 1 plus 2z plus z squared. So the relation, we observe that there is a relation. So for us, the H star polynomial is a sum over alcoves with covers. And then for Early and Kim is a sum over decorated order set partitions with exponent equal to the winding number. So we wonder if there is a bijection. And also Ognenu already showed that the number of decorated order set partitions of type Kn is exactly equal to the Eulerian number. Therefore, we come up with a way in the special case of delta 2n. So let A and A prime be two adjacent alcoves, then they would differ by this sort of, how to say, they intersect at the facets that are defined by the hyperplane yj minus yi equal to 1. And therefore, we want to label the facet by the chord ij. The lemma is that, I guess, for any choice of root, if both A prime and A double prime are covered by A, then the facets cross in the interior of the circle. Here is an example. So this is a way we can color code the chords. So if we have n chords that are intersecting mutually in the interior of the circle, then it will divide the circle into 2D arcs, and we can color them alternatingly, giving us a new decorated order set partition of type 2n. So here is a rigorous way to frame it. So we can define the map from alcoves in delta 2n to the decorated order set partitions such that if A covers A1 through AD in the breadth search order, then we send it to the decorated order set partition such that S1 is the union of every other arc in the circle divided by the D chords corresponding to the intersections between A and each of them. And then we show that the map phi A naught is a bijection from the set of alcoves that cover D alcoves to decorated order set partitions with winding number D. So here is an example. We show the dual graph of delta 2, 5, and since the two orange edges correspond to the arc, I guess 1, 3, and wait, what is it? Maybe 2, 4, and 1, 3. So the new decorated order set partition we get is 1, 3, 2, 4, 5. For tree positroids, so positroids are also labeled by planar bicolor graphs, which are Playboy graphs. When the Playbig graph of a positroid is acyclic, we call it a tree-positroid. The dual of a Playbig graph is a Playbig tiling, and tree-positroids are those positroids whose Playbig tilings are bicolored subdivisions. Here is an example. So a bicolor subdivision is a way to divide an n-gon into black and white polygons such that two adjacent polygons have different colors. We say that it has type Kn if any triangulation of the black polygons consists of k black triangles. So this is coming from, I guess, this part of the application comes from a paper by Parisi, Sherman, Bennett, Tesler, and Williams. So a partial cyclic order is a set of triples such that they satisfy cyclicity, asymmetry, and transitivity. A cyclic order is total if basically each triplet is comparable, and it is informally just a permutation cycle. We say that a total cyclic order extends a partial cyclic order if its containment inclusion as sets. A total cyclic order that extends a partial cyclic order is a circular extension of it. Majito, which is a computer scientist, he showed that there exists a partial cyclic orders without any circular extension. And to decide whether some partial cyclic order is extendable, this problem is NP-complete. So let tau be a bicolored subdivision. For each white polygon, we order the vertices around it clockwise, and for each black polygon, we order the vertices counterclockwise. We define the tau order to be the partial cyclic order, which is the union of the chains associated to the black and white polygons. For example, in this bicolor subdivision, we would have 1 to 7, 4, 5, 6 in clockwise order, and all the other stuff like around the black polygons in counterclockwise order. So Parisi, Sherman, Bennett, Tesler, and Williams showed that if we have a bicolor subdivision of type Kn, and then we take the corresponding positroid polytope, then the positroid polytope is triangulated by W simplices, where W is a circular extension of the sigma order coming from the bicolor subdivision. As a corollary, what we've shown is that our previous condition on this set of left cyclic descents exactly characterized the circular extension of the partial cyclic order, which comes from the bicolor subdivision. For half open, basically, we can remove facets of a polytope, and Ehrhart theory still holds, and we call that a facet of positroid polytope upper if it is of the form xij equal to k, such that the positroid polytope satisfies less than or equal to condition. Then if we consider this half open polytope, its H star polynomial is actually given by descent, so it is more, I guess, combinatorial. So compare with previous literature, if we remove the sum of coordinates equality from the definition of positroid polytopes, we obtain a Park-Taylor polytope. If we further require that all upper facets are bounded by 1, then we obtain a consecutive coordinate polytope defined by Eyer and others. So they showed that the H star polynomial of consecutive coordinate polytopes are given by descents of permutations coming from the circular descents from the circular extension of a partial cyclic order. So from the characterization given by descents of half open, we can compute the H star polynomial of the closed polytope by this inclusion-exclusion formula coming from the phase pole sets. Here we just like show this. I think this formula is probably known, but just to make it explicit, so we can compute the Mobius function and then the H star of each of the faces, and then have a little factor of 1 minus z to compensate the dimension difference. Here is an example. We show this pyramid from previous pictures, and we have 3 upper facets colored in orange, olive, and blue. Then the face pole sets with respect to these faces looks like this, and the Mobius functions are shown on the right-hand side. If we want to compute the H star polynomial of the whole positroid polytope that is closed, we can do this inclusion-exclusion where the top one corresponds to 2z squared because the descents are both of the descents are equal to 2, or both of the descents are equal to 1. And then we minus plus 3, 1 minus z, because plus comes from the Mobius function minus 1, and then minus 2 of the blue facets compensated with 1 minus z to the square, and we get 1 plus z. So thank you. This is all. Is the reference.
Hey, let's thank Yuhan. Questions for Yuhan?
Oh, I saw something in the chat. Oh my God, I didn't know that when I gave the talk, I could look at the chat.
Well,
Sorry.
mostly people answered each other's questions in the chat, which was very good.
Okay, great. Thank you. Oh, the real rootedness.
There was
Yes,
a question about real rootedness, yeah.
right. So I think Spencer told me that this is an open question, and we were trying to like look into it. I tested some cases, and I would say I believe that positroid polytopes have real rooted H star polynomials, but I can't say I know how to show them. I don't know. Yeah.
Can you also say, does this show you something about the positive geometry for these positroids?
So I guess this part I haven't explored them yet. Right. Can you elaborate? Like, what do you mean?
The reason I care about positroids usually is because of the way they're stratifying the totally non-negative Grassmannian. And I wonder whether these Ehrhart polynomials tell you something on that side.
Yeah, I guess in the paper of Lam and Posnikov, they showed that alcove polytopes of type A, C, and D4 are exactly those alcove polytopes whose Ehrhart polynomial is equal to the Hilbert, like the numerator of the Hilbert series of the corresponding toric variety. But somehow it's only for type A, C, and D4, and yeah.